In this video, we continue looking at trigonometric equations, and we will look at examples where we use the square identity, double angles, or compound angle formulae. Now, in this first example, we are told to solve for theta if 3 cos theta all squared minus 5 sin theta minus 1 equals 0. If you look at this equation carefully, you notice that the angles are the same, but if you were to try to factorize this, it would not be able to factorize. Okay, so when you come across an equation that has cos and sine in it, first check whether the angles are the same, and then try to factorize. If you can't, see if you can have cos on one side of the equal sign, sine on the other, divide by cos, turn it into the quotient identity, and continue from there. If you cannot do either of those, see if you can use the square identity. Now, the reason why you would want to use the square identity is to change one of the trig functions into the other, so that you ideally end up with a trig equation that has only one trig function. Okay, so looking at this, I have cos theta all squared. So I would like to replace the cos theta all squared with the cos theta squared equals 1 minus sin theta squared version of the square identity. Okay, that gives me 3 times 1 minus sin theta all squared minus 5 times sin theta minus 1. Right, I simplify this, so I get rid of brackets. So that gives me 3 minus 3 sin theta squared minus 5 sin theta minus 1 equals 0. I still have like terms, so I continue simplifying. So I have negative 3 sin theta all squared minus 5 sin theta. 3 minus 1 is positive 2. Right, I now have a trinomial that has only sin theta as my variable. Okay, it's a variable because the theta can change. So we need to factorize this. Now, I'm going to divide by a negative 1 to not have a negative exponent to the term in which I have a square sin theta. Okay, so I've got positive 5 sin theta minus 2 equals 0, having divided through by negative 1. Now, you are more than welcome, if you understand how to factorize, to go straight ahead and factorize. If you would struggle to factorize that, convert it into in terms of k. Okay, so if sin theta is k, then we would have this as 3k squared plus 5k minus 2 equals 0. This you should be able to factorize more readily. 3k, k, so my factors are 2 and 1, so if I have 3 times 2, that would give me positive 6, minus 1 would give me negative 5k. So my middle term would become 5k, last term would be negative 2. So then factorize, once you factorize that, write it back in terms of sin theta. So we would have 3, instead of k, now I have sin theta minus 1 in the second bracket. Instead of k, I have sin theta plus 2. Right, it's fully factorized, so I take each factor and make it equal to 0. So I have 3 sin theta minus 1 equals 0. Solve for sin theta. Okay, so I'm going to add 1 and then divide by 3. So that gives me sin theta equals a third. Now remember that our goal with trig equations is always to get to the point where we have one trig function equal to a value, because then we know how to carry on with finding the general solution or the specific solution. Okay, first determine your quadrants. So sine is equal to a positive value here, so we are looking at quadrants 1 and quadrants 2 where sine is positive. Find your key angle, and to find the key angle you would put shift second function sine of a third, and that would give you a value of 19,47 odd, so that rounds off to 19,5 degrees. So in quadrant 1, our angle theta is equal to the key angle plus multiples of the period of the sine graph. in quadrant 2, our angle theta is equal to 180 degrees minus the key angle plus multiples of the period of the graph. And that simplifies to 160,5 degrees plus k times 360. Okay, so we have two general solutions there. And don't forget that you have another factor. So we also have that sine theta plus 2 equals 0. Solving for sine theta, I have sine theta equals -2. And again, here we have our one trig function equal to a value, and we can try solve. Okay, now, if you were to try find the key angle for this, your calculator would tell you that there is an error. Okay, and the reason for that is there is no solution to this trig equation here. And the reason there is no solution is that the maximum value of the sine graph is 1. And the minimum value is -1. Okay, so just to look at that quickly. Okay, I'm not going to draw the whole thing, but the sine graph sits there, okay? It doesn't go above 1, it doesn't go below -1. So if we are looking for points of intersection between the graph sine theta equals y and the line y equals -2, there are no points of intersection. So there is no solution, okay? And all you would have to write here is straight away write no solution, and that's it. You don't have to draw the graph, no explanation, nothing. And the reason you would know that is knowing the maximum and minimum values of the sine graph. Okay. We now look at an example that requires the use of double angles. So we are told to solve for theta if sine 2 theta equals cos theta. Now, look at the angles. Straight away we notice that our angles are different. I have sine 2 theta and an angle of theta. So 2 theta and theta. My angles are different, so I must expand to try get the same angles. Okay, so I have a sine double angle here. So I'm going to expand, and I have 2 sine theta cos theta equals to cos theta. So now I have a trig equation with a sine and a cos. There are different options available to me with these types of equations. The first thing I want to try to do is see if I can factorize. To factorize, I need 0 on one side, so I bring everything to the other. So I subtract by cos theta. Looking at this, I can indeed factorize because I have a common factor of cos theta. Okay, having factorized, I now make each factor equal to 0. And I'm going to solve for sine theta here by adding 1 and dividing by 2. Okay, so now I have brought both factors to the point where I have one trig function equal to a value, which allows me to continue to find the general solution. Okay, now looking at the first one here, cos theta equals 0. Okay, now 0 is a significant point because that's where the graph of cos theta has its x-intercepts. So if you know the graph of cos theta, you could straight away know the answer to this as being theta equals 90 degrees plus k times 180 degrees, where k is an element of integers. Okay, so you could go the traditional route where you look at the key angle and work in the quadrants where cos is positive. So if you're looking at 0, just consider it as the quadrants that are positive, okay? And continue from there, and you would get two solutions which can contract into this one. Just quickly looking at the cos graph though, 90, 180, 270, and so forth. Negative 90, negative 180, negative 270, that's a 2, 1, negative 1, okay. Our cos graph sits there, okay. So our x values where y is 0 are negative 90, negative 270, 90 degrees, 270. So if you look at the 90 degrees, and if you add multiples of 180, you get the rest of the values. Okay, so if you know your graph, it's very quick and easy to find the solution. Right, looking at the other factor, that gave us sine theta equals a half. Okay, here sine is equal to a positive value, so we're going to work in quadrants 1 and quadrants 2. Find your key angle, and our key angle is 30 degrees. So in quadrants 1, our angle, which is theta, is equal to the key angle plus multiples of the period of the cos graph. Sorry, this is the sine graph. Okay, in quadrants 2, our angle theta is equal to 180 degrees minus the key angle plus multiples of its period. And this simplifies to 150 degrees plus multiples of 360. So 2 more general solutions to this initial equation. Right, now we have an example that requires the use of a double angle and other identities. So this is where it starts to just pull in all the tools and techniques that we've learned so far. It says solve for x if 1 plus sine 2x minus 4 sine x all squared equals 0. First thing, look at the angles, and you will notice that the angles are different. I have 2x and x. So I will have to expand this sine 2x in order to get the same angle throughout. Okay. The other thing I notice is that I do have only sine x's. Okay, so I've got the same trig function, but of course now when I expand this double angle, it's going to introduce a cos. Okay, but let's do that first. So I'm going to expand the double angle. So sine 2x gives me 2 sine x cos x minus 4 sine x squared equals 0. Right, so what this line has done is provided me with the same angle throughout. But the problem that it has brought in is the introduction of cos x. Okay, so if I look at these 3 terms, I cannot factorize. So I need to use something that will allow me to factorize this. Okay, so look carefully, and we see that we have a 1. Okay, now remember your square identity says that sine x all squared plus cos x all squared equals 1. So in place of 1, we can substitute the sine x all squared plus cos x all squared. Okay, let's see what that gives us. Plus the 2 sine x cos x minus 4 sine x all squared equals 0. Looking at this, we have a like term. So I'm first going to simplify and add my like terms. So I have cos x all squared plus 2 sine x cos x, and then I have 1 sine x all squared minus 4 sine x all squared, which leaves me with negative 3 sine x all squared. Okay, now what we have here is a trinomial that we can factorize. Now it will take practice for you to get your eye in to see this clearly and be able to factorize. But what you can always do is write it in terms of a variable. So let's say let a equal cos x and b equal sine x, and just rewrite it in terms of a and b. So this would be a squared plus 2ab minus 3b squared equals 0. And this you can more readily factorize. So a will be our first term in each bracket. Then I will have a 3b and a b as my second term. Now my middle term is positive 2, so I'm going to have positive 3ab, and then I'm wanting to subtract 1, so to give me the positive 2ab. And my final, so my final term would give me negative 3b squared. Okay, so that's the factorized form. So we substitute back. I've got two brackets. A was cos x plus 3b, so b was sine x. Then I have a, which is cos x, minus b, which was sine x. Okay, so fully factorized, and what I'm going to do is write each factor equal to 0 and solve. So I have cos x plus 3 sine x equals 0, and here I have cos x minus sine x equals 0. Okay, looking at the first equation here, I have cos x and sine x in this equation. Now, in the case where I have a cos x or sine x, I want to either try factorize, but I cannot factorize here. Then I'm going to see if I could use the quotient identity. So write cos and sine on opposite sides of the equal sign. So I'm going to subtract cos x, divide by cos x. So I'm going to divide by the cos x on both sides. Okay, so then divide by the coefficient of the sine x over the cos x. So I'm going to divide by 3. So I'll have sine x over cos x equals, the cos x is cancelled there, so it's negative 1 divided by 3. Now sine x over cos x, we know from the quotient identity, is equal to tan x. Okay, right, and now we have our one trig function equal to a value, so we can solve. So the negative tells me that I am working in quadrants 2 or quadrants 4. Okay, but remember the period of the tan graph is 180 degrees, so we only need one of these quadrants because the quadrants are 180 degrees apart. Okay, so my key angle is, okay, remember that when you have a trig ratio equal to a negative, that negative only tells you the quadrants that you're going to be working in. You do not include it in your calculation of the key angle. So what you would put into your calculator is arctan of positive a third, and that would give you 18,4 degrees. Okay, so working in quadrant 2, my angle, which is x, is equal to 180 degrees minus 18,4 degrees plus k times the period of the tan graph. Okay, and that simplifies to 161,6 degrees plus k times 180 degrees. Okay, right, looking at the second factor that I had here, again I've got an equation with cos and sine. I cannot factorize, so I try use the quotient identity. So I want cos and sine on other opposite sides of the equal sign. So I'm going to add sine x. Then I'd have to divide by cos x. You're always dividing by cos x because you want the sine x over the cos x. Okay, so divide by cos x. Sorry, that shouldn't be there. Okay, this cancels to give us 1, and we have tan x from the quotient identity. Okay, so now we can find our key angle because we have our one trig function equal to a value. Okay, so our key angle, tan x is equal to 1, is a significant point on the tan graph. That is where x is 45 degrees. Now, 1 is a positive value, so we're looking at quadrants 1 and quadrants 3, where tan is positive. But again, because of the period of the tan graph being 180, we only need one of these quadrants. So, quadrant 1, my angle x is equal to the key angle plus multiples of the tan graph, which is, the period, so 180 degrees, where k is an element of integers. Right, our final example is an example of an equation involving compound angle formulae. Now, this we use when we notice that the angles are different And we have a pattern of a compound angle formula in the equation. So it says solve for A, and we have cos A cos 24 degrees plus sine A sine 24 degrees. So we notice we have cos cos, sine sine. That reminds us of the cos double angle formula. Sorry, not double angle, compound angle formula. And then I have A 24, A 24. So my first angle is going to be A, my second angle will be 24. And we have to remember that for the cos compound angle formulae, the sign changes. So where I have a plus in the expanded form, I have minus in the brackets. Okay. Right. Now we have our one trig function equal to a value, so we can find the key angle and continue. Notice that this is my angle, and it is a compound angle, but we do not touch it until we get to working with the quadrants. Okay, so my key angle I find by putting arc cos 0,715 into my calculator, and that gives you a value of 44,4 degrees. Now our quadrants is where cos is positive, so that will be quadrant 1 and quadrant 4. Okay, so in quadrant 1, my angle. Now my angle is A minus 24 degrees. So this is where the full angle becomes important. Okay, angle equal to the key angle, which is 44,4 degrees, plus k times the period of the cos graph. K is an element of integers. Solve for A. So you're going to be adding 24. So add 24 to the 44,4, and that gives you 68,4 degrees plus k times 360 degrees. So there's your first general formula. When we look at quadrant 4, our angle, which is A minus 24 degrees, okay, is equal to, in the fourth quadrant, 360 degrees minus the key angle, plus k times the period of the cos graph, and we simplify. Okay, so we want A on its own, so I'm going to add 24. So I'll be calculating 360 minus 44,4 degrees plus 24 plus the k times 360. And that gives us A equal to 339,6 degrees plus k times 360 as our final general solution.